Hey scholars, it's good to be back with you. Today I'd like to talk to you about how to calculate the power required by a plane in level flight. If we're going to do this, help staff a plane, got one right here. This is my little radio-controlled airplane that I fly. It's winter right now, so it's in the hangar now. I'll fly it again when the weather turns better. But this is typical of little airplanes and big planes. The physics that apply to the little planes you see flying around apply to this just fine. So this is a good example. And this has got wings, okay, that make a lift force and a tail to keep it stable and landing gear and all that kind of thing. And you can maybe not see it, but there's a little motor back here and a pusher propeller back there. That's what makes the plane fly. Nice thing about having the propeller in the back is when I have hard landings, I don't crunch the propeller that way. So when I'm in level flight with this thing, well, I'm not flying, I'm flying it remotely. I'm not actually in it. The wings make lift that equal the weight, and there's a drag force. And remember, there's two kinds of drag. There's form drag, which is just, when you get right down to it, really the shear stress of the air flowing past the surfaces of the plane. And there's also induced drag. And induced drag is drag made by lift. So if the plane's going to fly, wing must be making lift because of the angle it makes with the air coming in, the angle of attack. And that induced drag gets added to the form drag. And so this motor back here, this battery-powered motor and propeller, has to make a thrust this direction to counteract that drag. So when the forces on the plane are in equilibrium, that is, lift equals weight and thrust equals drag, it's in steady level flight. Well, with that knowledge and a little bit of an expression describing lift and drag, we can figure out how much power is required to maintain level flight. So let me put this down. So what I want to do here is I'll work it out on the board, and then we'll go over to my computer and we'll crunch some numbers using either MATLAB or MathCAD. Okay, here we go. So if the plane is in level flight, the drag is equal to CD 1/2 rho v squared s. In case you don't know what these are, okay, CD is the drag coefficient, non-dimensional number that just describes how hard it is to get the airplane to go through the air. 1/2 is just a number. Rho is the density of air. Rho is about 1.2 kilograms per cubic meter if you're not too far above sea level. Velocity is just that. And S is wing area, and that's wing, it's called planform area. It's the area you see when you look down at the top of the plane. Well, that's okay. But I mentioned there's two components to drag coefficient. Let's unpack that a little bit. Okay, so the total drag is what we're calling the form drag, and that's CD0. That means it's the coefficient of drag at zero lift, times this thing right here, and this is a parabola, that's CL squared, so the coefficient of lift squared, divided by pi EAR. Well, pi is just a number. E is a number that measures basically the efficiency of the wing. It's called the Oswald efficiency factor, or span-wise efficiency. So for the wing on my little airplane over there that's not really tapered very much at all, E is probably in the neighborhood of 0.8 or 0.9. If you want E to equal 1, you need an elliptical wing. So go back and look at maybe a Spitfire from World War II that has this beautiful elliptical wing. Now, we don't tend to make elliptical wings much because they're hard to build. Every rib is different than every other. And since the leading and trailing edge are both curved, there's no straight lines anywhere on that wing. So they're hard to build. And this little stylized AR here is aspect ratio. Now, if the wing's just rectangular, aspect ratio is span divided by chord. If it's not rectangular, like that one over there, aspect ratio is span squared over area. So we'll figure that out here in a little bit. So this is okay. Let's make this is the thrust, okay, made by the propeller. Now what I'm looking for here, let's map out our path here. I've got thrust and I've got drag. What I'm really looking for is an expression for the power required for level flight that's a function only of velocity. Well, let's start working towards that. Let's substitute this in right there and see what we get. So hang on a second. Okay, I'm closer. But there's that CL squared there. Well, I don't want CL, I want velocity. Well, we've got an expression for lift as a function of CL and velocity. Let's take a look at that for a second. If there's CD and there's a drag there, so lift is CL 1/2 rho v squared S. Well, I ought to be able to solve that for CL, shouldn't I? By the way, lift has to equal the weight because we're in level flight. So let's just take care of that right now. CL looks like it's going to be 2W v squared S. All right. That looks okay. So that expression right there is going to get substituted in right there. Well, get substituted in down here. And I'm going to have an expression that's for thrust required that's only a function of velocity and some of these other things, but it isn't going to have a CL in it. So let's just go ahead and plug that in, substitute it in. There. Now I can clean this up a little bit, but now I've got an expression for the thrust that's a function of weight, velocity, area, things like that, but it's not a function of lift coefficient. So I can now plot this as a function of velocity only, because velocity is my independent variable and thrust will be my dependent variable. Well, thrust is great, but that's not what I need. I need power. Well, I need power for that. So let's pause for a second. Why do I need thrust or power? Well, it depends on what kind of engine you've got. Jets are assumed to make constant thrust, and piston engines are assumed to make constant power. So because that's where piston engine propeller planes are make constant power. So I'm going to assume that motor over there makes constant power, not constant thrust, because the thrust will vary with speed. So I really do need power. Well, this board's getting a little busy here. I'm going to erase it, and I'm going to write the expression for power here. Before I do that, what is power? Power is just a force times a velocity. Well, there's the force, thrust. All I've got to do to turn thrust into power is multiply it by velocity, and I'll have it. So give me a second here. I'm going to erase some stuff and rewrite the equation for you. Just give me a second. Okay, now I've got power as a function of velocity, and velocity appears cubed there and squared there. Well, we can clean it up a little bit, but that's probably about where we need to be right now. So now that we've got this, let's make a plot. I'll go ahead and do this on my computer. I have MathCAD fired up right now, so I'll probably do it in that. All I need to know is numbers for these various parameters, and these like CD0 weight, wing area and all that sort of thing. Those are unique to each plane, and you either look those up for a plane, or if you're designing a plane, the act of designing a plane in part means finding those things. So one way or the other, you're going to know that. So let's go crunch some numbers.
So here we are on my computer, and we're using MathCAD Prime version 8. Now this is certainly the easiest way I know of to beat numbers out of a computer. MathCAD Prime is kind of like a math scratch pad, so you can write equations on the screen kind of like you would on a sheet of paper. It's not as powerful as MATLAB, but it's a lot easier to use, and it's pretty well suited for problems of this size. So what I did here on top, at the top of the sheet, is I defined all the parameters we need for an airplane. Now this isn't any particular airplane. I kind of started with a Cessna 172 and modified things to make the numbers round pretty much. You'll notice that I have the numbers defined in metric units but also displayed in English units. MathCAD is really good at tracking units and converting units. So you can just type in numbers in whatever units you happen to have. I think it probably converts everything to metric units internally and then just displays them in whatever units you want. So let's find the power required for level flight. And we'll start right here with this expression for thrust required, which is what I had on the board a little bit ago. Now to get to power required right there, I just multiplied through by velocity and did a little algebra. This doesn't look exactly like the equation I had on the board, but it is. Now for minimum power required, I set the derivative of power required equal to 0 and solve for V min. Now the derivative with respect to V is pretty simple to write down, and you can see right here I just solve for V min. The only funny part about it is there's a fourth root there. It's pretty rare to see fourth roots in anything, but here we are. And the last thing I did is I defined a range of velocities to plot, starting at 20 meters a second, going up in steps of 2 to 80. And there's the plot. Now I have to confess I'm old, well, older than my students by a lot, and I still think in terms of miles an hour. I probably shouldn't, but I do. So in order to make sense of this, I had to convert everything to miles an hour over here, which is not a big problem for MathCAD. It's pretty good at that. So you can see the maximum predicted speed for this plane is around 73 meters a second. That's the point at which it takes 140 kilowatts to push it through the air. Now, when I said the power was 140 kilowatts, the power available, it's important to note that that's the amount that actually gets to the air. The propeller is the way that the power from the engine reaches the air, and the propeller is not 100% efficient. Its propellers on light aircraft are probably 80 or 90% efficient. So I started with the brake horsepower of the engine and then reduced it a little bit to account for the efficiency losses in the propeller. That's where the 140 kilowatts came from. And it looks right here like the minimum power required to fly happens at about 29 meters a second. And sure enough, there it is. So if you're flying along at 29 meters per second, you're using very little of the power of the engine, and all the rest of it can be used for something else. You can just steam along here if you want. You're not going to be going very fast, but you're not going to be using much power either, which means you're also not going to be using much gas. Or if you want to maximize the climb rate, you want to maximize the amount of power you have left over from that required to fly. Well, that happens right here. So given the numbers I have here, the maximum predicted climb rate would happen at 29 meters a second, because that's the speed at which there's the most power left over from the engine. So this is a pretty simple calculation, and the curve is easy to interpret. So I hope this helps, and we'll talk to you next time.